Chemical Kinetics, Part 5, presented by G. Satyanarayana Gaur, Assistant Professor, Department of Chemistry, Dr. BRR Government College, Jadcherla. In this discussion, we learn about kinetics of second order reaction, kinetics of third order reaction, half-lives of second and third order reactions, and methods to determine the order of reactions. Let me discuss about the second order reaction. So what is second order reaction? The reaction of which the sum of powers of concentration terms is equal to 2 in its rate equation, that is called as second order reaction. The sum of powers of concentration terms is equal to 2. The type of reaction we say it is second order reaction. Let's consider a reaction A gives B or 2A gives B, let's say. How can I express the rate of reaction? Minus d of A divided by dt is equal to K into A power 2. A concentration power 2. So in this equation, the sum of powers is equal to, it is 2. That's why we say it is second order reaction. We say it is second order reaction. Now in this case, same reactant is present. There is A only present. Only one reactant is present. And it is following the second order reaction. In some other cases, we can see two reactants will be present, like A plus B gives C. Two reactant A and B. Suppose 1 mole of A is reacting with 1 mole of B to give C. C is nothing but the product. If X concentration of A is participated in the reaction in definite time interval, in the same time, X mole per liter of B will participate in the reaction, since their number of moles are equal, that is 1:1. So that we can write the rate equation as minus dx divided by dt is equal to K into A minus X into B minus X. Remember, A minus X is the concentration of A at time t, and B minus X is the concentration of B at a time t. Okay, so we can express the rate of a reaction when only one reactant is present or two different reactants are present. Let me discuss about the kinetics of second order reaction where only one reactant is present. For that we write it is minus dc by dt is equal to kc square. Minus dc by dt is equal to kc square. We are writing that equation depending on this. So instead of concentration of A, now we are writing C. So minus dc divided by dt is equal to kc square, we can see. So here the reactants are taken. X moles of reactant is consumed in the time t. So X is this one. Next, let me derive the equation for second order rate constant. Second order rate constant. Now we are shifting the concentration terms at one side and time towards, what is that, right side. Concentration terms towards left side and time term towards right side. Then we will get the equation. That equation is now integrated. It is a minus integral of c square dc by dc square is equal to k into integral of dt. How to see the limits? When time is equal to 0 means in the beginning of the reaction, we say the concentration of reactant is A. We say it is initial concentration. When time is equal to 0, A concentration of reactant is present in the reaction of second order reaction. If the time reaches to T, now X amount of reactant is consumed in the reaction. So the amount of reactant left is, or concentration of reactant left is A minus X. So T is equal to 0 to T are the limits of time, and A to A minus X are the limits of concentration. So in integration process, you see integral of dc by c square, integral of dc by c square. This integral of dc by c square is nothing but it is 1 by c minus of 1 by c. Integral of dc by c square is equal to, what to say, it is minus 1 by c. Now we are applying the limits. Minus of minus 1 by c, A to A minus X, that is equal to integral of dt. All of you know that it is t. K into t from 0 to t. Let me apply the upper limits and lower limits in this. What we get here in minus into minus gives plus, so 1 by a minus x minus 1 by a is equal to kt. So we are writing equation for k. K is the rate constant of second order reaction. K is equal to 1 by t into 1 by a minus x minus 1 by a, where the t is the time of reaction, k is the second order rate constant, a is the initial concentration of reactant when time is equal to 0, x is the amount of reactant consumed in the reaction in the time t. Like this we can derive the equation for second order rate constant. So this equation is applicable to the reaction where only one reactant is present. That is important. Okay. Next, let me see about the next case. When two different reactants are present in second order reaction. Just now we were saying that A plus B gives C, like that. Two different reactants are present. Then what we write? The rate law is equal to dx by dt is equal to K into concentration of A into concentration of B. A and B are the reactants. And in this reaction, suppose if small a and b are the concentrations of A and B in the beginning. Small a is the concentration of A and small b is the concentration of B in the beginning when time is equal to 0. So when x moles of reactant A is participating in the reaction, in the same time x moles of what B will participate in the reaction, because the number of moles will be same in the reaction in the stoichiometric equation. So after time t, now the remaining concentration of A and B will be A minus x and B minus x. So that we can write the rate law as it is dx by dt is equal to K into A minus x into B minus x. As we did in the case of what second order reaction where only one reactant is there. Similarly here also we shift the concentration terms towards LHS and time towards RHS. When we shift this A minus x and B minus x towards LHS, what happens is dx by A minus x into B minus x. That is equal to K into dt. Okay, means the concentration terms are represented towards left hand side and time factor is represented towards right hand side. Now integrating this equation within the limits of 0 to t for time and A to A minus x for the concentrations. Is it A to A minus x is the concentration, or actually you have to say what A to A minus x, because A and B are the different concentrations, so you have to write it is 0 to x, you have to say it is 0 to x. They are the limits, because when t is equal to 0, x will be 0, and when t reaches to t, that is time is t, then the amount of reactant consumed will be equal to x. Now this equation is solved by the method of what? Partial fractions. This fraction should be converted into partial fractions. Based on that we can solve this equation. So finally we get what? K is equal to 2.303 into t into A minus B log B into A minus x into A into B minus x. Do you know what are small a and small b? They are the initial concentrations of capital A and capital B when time is equal to 0, where x is the amount of either A or B that consumed in the reaction. K is the second order rate constant. So by partial fraction method, we can solve this integration equation. Okay, next let us see about the reaction. What we get is K is equal to 2.303 into T into A minus B log B into A minus x into A into B minus x. Now we were discussing about the pseudo first order reaction in previous cases. What are the examples of pseudo first order reactions? It may be inversion of sucrose or hydrolysis of ester. Why they are pseudo first order even though they are containing two reactants? Because if one of the reactant is, that is water, is taken in excess, then the rate of reaction depends on only one concentration term. So in this one, two reactants are present, that is A and B. For example, A is taken in excess. Then the rate of reaction depends on only B. Means the second order convert into first order. The second order reaction convert into first order under which conditions? If any one of the reactant is taken in excess. So in this situation, A is taken in excess. So let us substitute, see the situation B in this equation. So K is equal to 2.303 by T into A minus B log B into A minus X by A into B minus X. In this equation, if you see A is taken in more excess. That's why what we can do, X can be neglected. This can be neglected. Means BA will be there. BA into A into B minus X. And BA into BA divided by A into B minus X. That is K is equal to 2.303 by T into A minus B log BA by A into B minus X. Here A and A will get cancelled. Finally, we get what K is equal to 2.303 by T into A minus B log B divided by B minus X. It is identical with which equation? K is equal to 2.303 by T log A by A minus X. Means in second order reaction, if more than one reactant is there, under that condition, if any one of the reactant is taken in excess, then the rate depends only on one reactant. Then what happened? The second order reaction will convert into first order. Means if the reaction follows first order kinetics and becomes pseudo first order reaction. Is it clear? So like that we can understand the kinetics of second order reactions. Let me see about the half-life of second order reaction. Derivation of equation for half-life of second order reaction. Whenever you derive the half-life representations, first of all we consider the equation for rate constant. Here the equation for rate constant of second order reaction is taken where only one reactant is present in the reaction. K is equal to 1 by T into 1 by A minus X minus 1 by A. In this, when time reaches to T off means half-life. As we discussed earlier, X becomes what? Half of the initial concentration. We said initial concentration is A, so that X becomes A by 2. A by 2 of concentration of reactant will consume in the reaction. By substituting this, T is equal to T off and X is equal to A by 2, now we can see how we get K is equal to 1 by T off. Instead of T, what you are writing? T off you are writing. Instead of T, you are writing T off. This T is replaced by T off. Whereas A minus X becomes A by 2 minus 1 by A. And simplifying this, we get K is equal to 1 by A into T off, or T off is equal to 1 by Ka. This is the equation for derived for half-life of second order reaction. T off is equal to 1 by Ka. From this what we understand? The T off is inversely proportional to concentration of reactants. Half-life of second order reaction is inversely proportional to concentration of reactant. Means when the concentration of reactant is increased, T off will decrease and vice versa. Both half-life and initial concentration are related inversely proportional. That is very, very important. Means if the concentration increases by n times, T off decreases by n times. The type of relation is there between the half-life and concentration of reactants. Okay. Next we see the graphs regarding second order reaction. What about the rate? Rate depends on what? It is concentration of A power 2. It is a linear relation. Is it? Because rate is equal to K into concentration of A power 2, we said. It is present in the form of what? Y is equal to mx. Similarly, T off is inversely proportional to 1 by A. That's why it is also a linear. There is also linear relationship. T of and 1 by 8 gives a straight line where slope is equal to 1 by k and x by a into a minus x. X divided by a into a minus x versus t also a straight line passing through origin where slope will be equal to k. Hence, with the help of the equations, we can understand all these are present in the form of y is equal to mx. By writing the equations in proper way, we can understand these graphs very well. Okay. Yes. Now we see the third order reaction. What is third order reaction? It is a reaction in which the sum of powers of concentration terms is equal to 3 in rate equation. That reaction is called as third order reaction. The sum of powers of concentration terms in rate equation will be equal to 3. So then how can we represent when a same reactant is only one reactant is present in the reaction and it follows the third order kinetics? We represent like this. Minus d of a divided by dt means rate. This is the rate. Is equal to k into concentration of A power 3. Is it? Next, if equimolar concentrations of A of all the reactants, that is 3 reactants are taken, and so x moles of reactant is consumed the time t. Or let's say we can represent like this also. You see, instead of concentration of A, we are writing what C, that is minus dc by dt is equal to kc cube, where C is nothing but what? C is nothing but what? Concentration of A. In the similar way, what happened in the as we did in previous case, now you bring all the concentration terms towards left side and time towards right side. So rearranging this equation, we get minus dc by c cube is equal to k into dt. Now when t is equal to 0, the initial concentration of reactant is A. When time reaches to t, the concentration of reactant will be A minus x. Mean the concentration limits are A to A minus x and the time limits are 0 to t. So we are integrating that equation within that limits. What is integral of that is dc by c cube? It will be equal to minus 1 by c square. Integral of dc by c cube. This value gives what? It is minus 1 by c square. It is minus 1 by 2c square, not c. It is minus 1 by 2c square. Okay, integral of dc by c cube is equal to minus 1 by 2c square. So now we are applying what limits is it? Limits. What are the concentration limits? A to A minus x. What are the time limits? 0 to t. Because you know integral of dt is nothing but t. Integral of dc by c cube is equal to minus 1 by 2c square. Integral of dt is t. We are applying the limits. And applying the limits here, minus and minus becomes plus 1 by 2 into 1 by a minus x square minus 1 by a square. Upper limit minus lower limit. That is equal to k into t minus 0 means we say it is kt. Now we are writing equation for k where k is equal to 1 by 2t into 1 by a minus x power 2 minus 1 by a square. This is the final equation we get, is it? In case of third order reaction, it is k is equal to 1 by 2t into 1 by a minus x power 2 minus 1 by a square. That is the rate constant for third order reaction. Like that, you see, if it is the third order, we got 2t. And what about the power? It is 2. Means 1 less than that order number. The third order. Third order means we get what? 2. What is the power of this concentration? 2. Like that, for nth order, we can derive this equation. K is equal to 1 by n minus 1t. K is equal to 1 divided by n minus 1 into t into 1 divided by a minus x power n minus 1 minus 1 by a power n minus 1, where n is the order of reaction. So this is applicable to the orders of second, third, fourth, and so on. Second and third order we can understand very well. There you have to substitute the value of n. In second order, you substitute n is equal to 2. So we get 1 by t into 1 divided by a minus x minus 1 by a. For third order, you substitute n is equal to 3, 1 by 2t into 1 divided by a minus x power 2 minus 1 by a power 2. Like that, we see the rate constant of nth order reaction also, where the same, only one reactant is present in the reaction and following the nth order. Let us see the half-life of third order reaction. We are deriving the equation for half-life of third order reaction. We know that in order to derive the equation for half-life, we start with equation for rate constant. So what is the equation for rate constant? K is equal to 1 by 2t into 1 by a minus x power 2 minus 1 by a square. Now we substitute t is equal to t of, then x becomes what? X becomes, that is, a by 2. And substituting, you see, t becomes t of, a minus x becomes a by 2. So we are substituting these t of and a by 2. So k is equal to 3 by 2 a square into t of, and t of becomes equal to 3 by 2 into k a square. So what is the relation? T of is inversely proportional to a square. T of is inversely proportional to a square. Is it? In the case of zero order, in the case of zero order, T of is directly proportional to A. In the case of first order, T of is a constant, independent of concentration of reactant. In the case of second order, T of is inversely proportional to A. In the case of third order, T of is inversely proportional to A square. They are the relations of T of in different orders of reaction. Here we have summarized these half-lives and half-lives of different orders of reactions and concentrations. In zero order, T of is directly proportional to A. In the first order, T of is equal to constant. In the second order, T of is inversely proportional to A. In the third order, T of is inversely proportional to A square. Depending on that, for nth order, we can generalize the equation. We can write the general equation for nth order. How the T of is related to the initial concentration? T of is inversely proportional to A power n minus 1. T of is inversely proportional to A power n minus 1, where n is the order of reaction. This is a very, very important concept so that we can solve many problems on this by observing the relation between T of and A, so that we can solve the problems related to half-life. For example, you see, if concentration is double, T of also becomes double. And both of them are directly proportional. We say it is zero order. We say it is zero order. If concentration is double, there is no change in half-life. We say it is the first order. If the concentration is doubled, half-life becomes half. If concentration is doubled, half-life becomes half. It is second order. If concentration is doubled, half-life becomes 1 by 4. That is third order. Like that, they are the relation between the half-lives and concentrations of reactant. And by observing just the data, we can determine the order of reaction. Now let me discuss the methods to determine the order of reaction. How to determine the order of reaction? Already we have discussed the order of reaction is nothing but the sum of powers of concentration terms in rate equation. How this rate equation is arrived? Based on experimental studies. Is it? So with help of experiments, we collect the data of that experiment. So with help of that data, we can determine the order. In order to determine the order, these are the methods. One is integrated rate equation method. Second is half-life method. Third is 1/2 differential method. Fourth one is Ostwald's isolation method we discuss. There are the four methods. Integral rate equation method, half-life method, 1/2 differential method, and Ostwald method. Let me discuss about the integral rate equation method. So we have derived the rate constant for each and every reactions which are following nth order kinetics. In the case of zero order, k is equal to x by t. What is the, in case of first order reaction, what is the rate constant? K is equal to 2.303 by t log a by a minus x is it. Log a by a minus x. This is log a by a minus x. A rate constant of second order reaction, k is equal to 1 by t into 1 by a minus x minus 1 by a. Like that also we can write for third order. So when we perform the experiment, there we collect the data. One, time, different time intervals. Second point, the initial concentration, that is when t is equal to 0, what is the concentration of reactant, that is A. Third is the amount of reactant consumed in the reaction, that is x, at different time intervals, so that we can calculate a minus x. So T is calculated, T is determined, A is determined, x is determined, so that we can determine a minus x. So by collecting this data, now we substitute the data in different equations provided for different rate constants. Is it? Then, so on substituting this, the integrated rate equation, which gives a constant value for rate constant by substituting this data at different time intervals, that indicates order of reaction. How it is? We collect the data experimentally, and this data will be introduced in the equations. Equation of zero order reaction, equation of first order reaction, equation of second order reaction, and we verify. If we get the k values recurringly constant at different time intervals with this data, that k value means either it may be the 0, first or second. That indicates the order of reaction. Means we have to check each and every equation whether we are getting the constant k values or not. The case where we get the constant k value, based on that we identify the order. That's why it is a time consumable method, and we say it is hit and trial methods. In this hit and trial methods, or in the hit and trial method, we can also draw the graphs. We have seen the different graphs which are drawn for different order of reactions. The graph which satisfies, or the case which satisfies the data, that represent the order of reaction. So this method is nothing but the hit on trial method. Okay, so this is the first method to determine the order of reaction. You see here the second case here, set 1, set 2, set 3, how we are collecting the data. You see, for hit and trial method, time is equal to 0, it is small a, initial concentration small a. Is it small a is same, set 1, set 2, set 3. When time is equal to 30 minutes, concentration of reactant 0.260. Is it? Time is equal to 30, a minus x, that is amount of reactant left over is 0.260. Like this we collect the data where time and concentration each represent it is what, a minus x. This is a minus x at 30 minutes, a minus x at 56 minutes, a minus x at 78 minutes. So now we introduce this data in the equations of different orders. So the case the instant where we get constant k, that represents the order. Like this data has to be collected and substituted in the equations for different rate constant. Next, second method is the half-life method. You know, the half-life is related to the initial concentration. How? Half-life is inversely proportional to a power n minus 1, where n is the order of reaction. For the same reaction, we perform the reaction such that we determine the half-lives for different concentrations. Means at different concentrations of same reaction, we determine the half-lives. So here we have determined the half-lives for A1 concentration and A2 concentration. Since the half-lives are inversely proportional to initial concentration or the concentration, we can write like this. T1 by T2 is equal to A2 by A1 power n minus 1. Can you observe here? T1 is inversely proportional to A1, T2 is inversely proportional to A2. Means we are calculating the ratio between two half-lives of a same reaction where the concentration of reactants are different. Okay, they are inversely proportional. Right? So now see here. So based on this, we can calculate the value of n. We can calculate the value of n. Is it by this equation you can calculate the value of n. For example, you see this case how the half-life is related. Again, we are discussing if zero order reaction is there, x becomes what? X by 2. In how many half-lives it becomes? One half-life. Now it is, example say it is 40 minutes. Now this x by 2 again becomes x by 4. In second half-life we are saying. Second half-life we are saying. Since the concentration is reduced to half, now the half-life time also reduced to half. Means now the 40 minutes becomes how much? 20 minutes. Means the concentration decreases. So that what happened? Half-life also decreases to half. The type of relation we see in the zero order, where the first order concentration reduced to half, but there is no change in the half-life because half-life is independent of concentration. That you can see. In the second order, when the concentration decreased to half, what happened? Half-life becomes double. Half-life becomes double. That is about the second order reaction. Just by observing this data also we can solve the problem sometimes. Otherwise, use this equation. So you substitute the half-lives of different concentrations of same reaction so that you can calculate the value of n. So this is, we say, half-life method. Okay, so here one problem is there, you see. For concentration is 0.1, it is 30 minutes half-life. If the concentration decreased to 0.05 means it is half. Now the half-life becomes double. Have you identified? Order is 2. Order is 2. Or you see the, you put in the equation T1 by T2 is equal to A2 by A1 power n minus 1. What is T1? 30 minutes. What is T1? It is 30 minutes. 30 minutes. T2 is 60 minutes. Is it? 30 minutes and 60 minutes. We are substituting half-lives is 30 minutes and 60 minutes is equal to inversely proportional. 30 minutes for 0.05 and 60 minutes for 0.1 power n minus 1. Okay, next 1 by 2 is equal to 30 by 60 means it is from this 1 by 2 is equal to again 0.05 by 0.1 means 1 by 2 power n minus 1. The bases are equal, so how to equate the powers? Means n minus 1 becomes equal to 1. If n minus 1 is equal to 1, what do we say it is? N is equal to 2. Like that, we can solve the problems to determine the order of reactions based on half-lives. Okay, so like this we can solve the problems. This is one of the example. Next is one of the example. Again you see what is the concentration of reactant? 0.4. Half-life is 64. Concentration decreased to half. 0.2. Half-life becomes half. Have I identified the order? Means concentration is decreasing by 2 times. Half-life is decreasing by 2 times. Concentration is becoming half. Half-life also becomes half. Means concentration is directly proportional to half-life. Have I identified the order? Yes, it is zero order reaction. It is zero order reaction. Otherwise, you put in that formula T1 by T2 is equal to A2 by A1 power n minus 1 and you solve for n, you will get it is 0. Third method is one-half differential method. In this method, we determine the rate of reaction at different time intervals. Suppose a reaction is there. We have determined the rate at 5 minutes time. Again, we determine the rate at, for example, let's say it is 25 minutes time. At the 5th minute, you are determining the rate. At 25th minute also, you are determining the rate. You know, as the time proceeds in the reaction, concentration of reactant decreases, rate also will change because the rate of reaction depends on concentration according to law of mass action. So two different reactants we are considering, that is C1 and C2. Let me write the rate equation for the reaction at C1 concentration and C2 concentration. When we write the rate equation for C1 concentration, it is minus dC1 by dt is equal to K into C1 power n. Because n you have to identify. We are saying the order is n. Sum of powers of concentration terms. Here the power is n. What is the concentration terms? C1. Similarly, for C2 concentration of same reaction or same reactant, again we write the rate equation as minus dC2 by dt is equal to K into C2 power n. N is the order of reaction. Now we are applying logarithms to these two equations. Applying logarithms. What we get in the first case? Log minus dC1 by dt is equal to log K plus n log C1. Similarly, in case of second equation, log minus dC2 by dt is equal to log K plus n log C2. Now we are subtracting equation number 1 or 2 from 1, whatever it may be. So log minus dC1 by dt minus log minus dC2 by dt is equal to n will be the common, because log K, when you are subtracting, this log K and log K will get cancelled. You see, when you are subtracting, what happened? This log K and log K will get cancelled. So minus logs minus dC1 by dt. From that you are subtracting second. You are subtracting what? 1 minus 2. Subtracting 1 minus 2 is 2 from 1. So log minus dC1 by dt minus log dC2 minus dC2 by dt is equal to, here I'm subtracting log K and log K will get cancelled. N will be the common in both of these factors. When n is the common, log C1 minus log C2. This equation we get. Okay, so this can be again written in the form of, because log A minus B is equal to what we said, log A minus log B is equal to log A by B, like that. Or you see, you can write equation for what we say it is n. You can write equation for n. On writing equation for n, what we get, you see, n is equal to log minus dC1 by dt minus log minus dC2 by dt divided by log C1 minus log C2. So based on this equation, you can determine the order of reaction. So what are the requirement here? You have to determine the order. Yes. So in order to determine the order, what are the requirements? 1. You have to calculate the concentrations, two different concentrations of same reaction at different time intervals. Second, at those concentrations, you have to determine the rate of reactions. You can determine the rate of reactions by drawing the graph between concentration versus time. From that graph, you can calculate this. Now you see this problem. Concentration of A, concentration of B, and concentration of C is given here. A, B, and C is given. So rate is given here. Okay, so let me see this case. Now the task is, we have to determine the order with respect to what? B. We have to determine the order with respect to B. In order to determine the order with respect to B, we select the sets such that concentration of A should be constant, concentration of C should be constant. Then by varying the concentration of B, so that you can see change in rate. Is it 1 and 2 sets, first and second sets? In these two sets, concentration of B is changing, whereas concentration of A remaining constant. So let you substitute in this equation. N is equal to log minus dC1 by dt. What is the rate in the first case? What is the rate in the second situation? Minus dC1 by dt, log 2.8 into 10 power minus 5 minus log 2.1 into 10 power minus 5. Is it? When 0. What we say it is 0.2 concentration is there. What is the rate? 2.8. You see, you can you observe here it is minus dc1 by dt in denominator c1. Where is the c2 and c2? C2 and C2, you see? 1 minute. So C1, C1, C2 and C2 means when you are substituting this rate, the concentration will be C2 will be this one. If this is C1, we say this is rate belongs to C1. This is the concentration of B, which is indicated as C1. By substituting these, what we write, we can calculate n value. We got n is equal to 1. Like this, we can determine the order of reaction with help of what we say rate of reactions determined for different concentrations. The fourth and last method to determine the order of reaction is the Ostwald isolation method. In this method, the initial concentration of one of the reactant is taken much less than the other reactant. For example, A, B, C are the example. A, B, C are the reactant. In order to determine the order with respect to A, B and C should be kept constant. They are kept constant. Otherwise, B and C should be taken in excess also. Under that conditions, the rate of reaction depends only on A. By changing the concentration of A, we observe change in rates. Depending on that, we can determine the order with respect to A. Similarly, in order to determine order with respect to B, how it is? A and C concentration should be kept constant by taking them in excess. Now we study change in concentration of B and change in rate. Based on that, we can determine the order with respect to B. We follow the same procedure in the case of C also. Like this, we decide or determine order with respect to each and every reactant. Then we will determine the overall order by adding all these individual orders with respect to each and every reactant. So we isolate a reactant by taking it in limited and remaining are taken in excess. This is about the Ostwald's isolation method. So in this discussion, what we have discussed, the summary is second order rate constant, derivation of equation for second order rate constant, half-life of second order reaction, and derivation of equation for second order rate constant when two different reactants are present, and derivation of rate constant for third order reaction, derivation of half-life for third order reaction, and also we have discussed methods to determine the order of reaction. Among that, one is heat and trial method or integrated rate equation method. Second is half-life method. Third is Van half method. Fourth is Ostwald isolation method. And we have seen some problems also. Thank you.